Okay. Okay, thank you very much, and thank you very much to the organizers for the opportunity to talk within this very nice workshop. And today I would like to present some work which is still in progress, but we hope to at least present the first part of it pretty soon. And it's about try to have a sort of geometric intuition. Sorry. Okay, how to get a geometric intuition of a formulation of three-dimensional Liger-spin black holes, and the work is in progress with Jonathan Lindgren, who is a student in Brussels that who is going to move to Nordita in fall. So let's start by somehow presenting to you which is the context I would like to work in, and the context is just three-dimensional gravity, and our main inspiration will be the Chern-Simons formulation of three-dimensional gravity, although in many respects we will try to throw it away and to have some alternative to what has been recently done in this context. So the main idea is that, well, it's well known since the 80s that one can rewrite up to boundary terms the Einstein-Hilbert action as the difference of two Chern-Simons actions, and these Chern-Simons actions are SL2R valued. So they contain connections which are SL2R valued, and so in particular our fields will have this expansion where these are just the SL2R generators. So this means that the gauge algebra is just the SL2R cross SL2R gauge algebra, and one go back to the Einstein-Hilbert action by defining the spin connection omega and the field by E in this way, which is kind of well known, and by now it's also kind of customary to consider extensions of this setup to include Eiger spins, and the main idea is that once you arrive at this kind of formulation of three-dimensional gravity, you can ask yourself what happens if you change the gauge algebra, and the answer is that, for instance, if you consider an SLNR cross SLNR gauge algebra, you describe an Eiger spin theory. Why that? Because you can branch you can pick up an SL2 subalgebra and branch the SLN algebra under the adjoint action of this SLN, and this will bring you to a branch of the algebra of this type, for instance, where these are just the SL2 generator, and here are the remaining generators that in this case belong to a spin 3 representation of SL2, and you can expand the fields, and essentially the coefficients of this expansion you can interpret them as being the dry-bind and the sort of Eiger spin dry-bind and so on. So that is the main setup. So, well, in general you can do it for SLN, but in this talk I will mainly focus to SL3 just for simplicity. So now, so this was the presentation of the actions, so was the presentation of the theory. Now, what happens if one consider what are the solutions of the equations of motion? So what are the solutions in the theory? So first of all solutions in this case, since we just have a Chern-Simons theory, are just flat connections. So essentially are just all flat connections that fits the boundary conditions. So how do you distinguish in equivalent solutions? They are specified by boundary charges and possibly by holonomies. And well, how you identify black holes in this context? The easiest way of doing is to identify a black hole as a solution which has specific thermal properties, and in particular as a solution which has to whom you can associate an entropy. So how can one do this kind of identification? Well, there is a way in the Chern-Simons formulation, and the main idea is to use the Euclidean formulation of gravity to work it out, to identify black holes. And in Euclidean gravity, a black hole is just a solution which has a topology of a torus, with a contractible time circle. And so essentially you can identify a black hole as being a solution whose base manifold in Chern-Simons has this particular topology and whose holonomy around the time circle is trivial, up to certain specification that appeared recently in literature, but I won't enter into these details. And the great advantage of this formulation is that it's perfect for generalization to higher spins. It only uses Chern-Simons data, and indeed the higher spin black hole solutions have been first proposed within this formulation by Gutler and Krauss in 2011, and this gave rise to all the subsequent developments in literature. But if we go back to gravity, actually there are many ways of characterizing a black hole solution. So one possibility is the one that we learn in textbooks. So just use the metric formulation, compute surface gravity, and try to compute the entropy, starting from this thing. And well, the main feature of the characterization of black holes in the metric formulation is that it is a solution who has an event horizon. And usually you identify this as being, a particularly congruence of null geodesics, so you need a metric in order to identify what is the horizon. And that is a kind of way that is not available in higher spins because the metric is not a gauge invariant object, and then it's kind of not suited to generalization. The other possibility is the one that I briefly recalled, is just that you define a black hole in the Euclidean formulation as being a solution to whom you can associate an entropy, and this is the way that has been considered in literature. But there is even a third way of understanding what is a black hole, at least in 3 dimensions, and it is based on the observation that locally all solutions of the field equations are locally isomorphic to anti-de Sitter. This means that a black hole at most can be a solution that you can obtain by identification of points in anti-de Sitter. So what I would like to explore during this talk is if it is possible to try to generalize this kind of geometrical description of a black hole. So just to briefly recall you how these things works. So the main idea, as I anticipated, is that all solutions of the equation of motions are locally equivalent to IDS3. So a black hole has been pioneered by Bagnados, Enot, Teitelbaum, and Zanelli, must be a solution that can be identified by suitable identification of points by a discrete subgroup of isometry group of anti-de Sitter. So this is the best that you can do if you want to define a solution which globally differs from the anti-de Sitter solution. Yes, this is true. So strictly speaking, you don't work with global IDS3, but you pick up a patch of anti-de Sitter. So I will kind of swap under the rug this kind of part of the story. This is true. So there are some conditions that the isometry, for instance, the Killing vector generating the isometry must satisfy some conditions of positivity, and these select a subspace of anti-de Sitter. So essentially in the following I will reformulate way in a things where I kind of work locally, in the sense that I pick up a patch which cover a region of anti-de Sitter, and this will be my good patch. So I will kind of not presenting, at least today, the more intrinsic characterization on how to choose the right patch. Essentially it will be a bit coordinate dependent, the presentation of today. But indeed, so that is one of the reasons why I'm coordinate dependent. So instead of just reviewing to fix the notation how to build a black hole, let me do something slightly simpler. So I just show to you how to characterize a point particle in anti-de Sitter, because the main idea is the same, but the kind of construction is slightly simpler. So the main idea is that, as I said, you just take a metric which is the anti-de Sitter metric. You don't have to cover the full global anti-de Sitter exactly for that reason, because typically you don't want to do that. And then you consider an isometry. So in this particular case, I want to, well, it's known that point particles are obtained are identified with conical defects in anti-de Sitter tree, or in flat space, essentially. And how can I build a conical defect? So I have to cut out a portion of the ADS3 space. And the idea is to consider an isometry of this type. So I consider both a shift in the angle and a shift in time. In this picture, somehow I visualized what happens if you consider a shift in the angle. Somehow you can draw two regions, and the fact that you identify this plane and this plane thanks to this isometry, and essentially by doing this identification you cut out this region of space. If you also want to give spin to the particle, you also have to consider a shift in time. Okay, so another trick that it will be useful in the following is that, okay, this is my isometry, but I would like to somehow let it act in a trivial way, at least for what concerns the t coordinates. And I can do this trivially, so just by redefining the t coordinate and introducing this quantity that depends on the two parameters that I have in the isometry. And if I introduce with new t coordinate, somehow my isometry acts trivially only in the angular coordinate. And this means that, well, essentially the range of phi is not from 0 to 2 pi. And but if I do this, the metric will change form, and then it's not clear how it represents. But I can try to show you that at the end I obtain a conical particle just by massaging the result that I obtain just by performing this shift in the coordinates. And well, this massaging the metric comprises a series of additional change of coordinates. They are not, well, the details are not particularly important. You can just trust me that if I perform this change of this chain of change of coordinates, I obtain a metric which looks like the one that you can find there. And you can notice that this is almost the metric of a BTZ, so it's almost the metric of a stationary solution. So in the sense that here I have a dt square, I have a d rho divided by a quantity which is the same that you can, a function of r of a radial coordinate, which is the same that you can see here. And essentially here I have the usual quantity that you find when your solution has a non-trivial shift. Okay, but so it looks like a BTZ black hole, but it's not yet a BTZ black hole because the range of the angular coordinate is not the correct one. Due to the identification of points, now my range goes from 0 to alpha. But this last point is easy to fix. You just rescale all your coordinates. After the rescaling of all your coordinates, well, if we introduce this quantity, I want to rescale the angular coordinates such to obtain the usual range. But in order to preserve the form of the metric in a BTZ-like form, I also have to rescale the radial and time coordinates. And at the end of the story, this is the final form of the metric that I obtain. And it looks like the BTZ metric with a crucial difference that the mass is negative. And this explains you why I'm describing a particle, because the particle somehow leaves well, point particles are considered to leave a sort of phase space of ADS3 gravity such this. So here you have the black holes, the BTZ black holes. Here you have anti-de Sitter. Here you have mass, and here you have angular momentum. And point-like particle lives in this region, and this is what I recovered with this tiny manipulation. So the main idea is to try to extend this class of this kind of manipulations to the higher spin context. But of course, well, at the very beginning I told you that I cannot characterize the solutions by using a metric, so in a sense I'm a bit cheating because here I'm using the metric actually. But there is a reformulation of this procedure that do not rely directly on the knowledge of a metric, essentially. And it is the fact that actually ADS3 can also be, is also isomorphic, at least locally, to an SL2R group manifold. And so the idea is to reformulate this procedure in terms of SL2R data as identification of points within an SL2 manifold. So this is not a new idea. Well, has been considered by many people. For instance, here I'm referring to the Matchul way of building the solutions. I'm not sure it's the first place where this has been worked out in details, but at least it's an interesting reference. And well, essentially, as you can understand by looking at this slide, the main idea will be to try to repeat the same story using SL3 instead of SL2 and try to characterize black hole solution also in higher spin theories by playing these tricks. So how can we see that we can formulate the space of solution of three-dimensional gravity in terms, it can be parameterized by an SL2R group manifold? So the idea, for instance, we can pass through the Chern-Simons formulation to see these. So ADS3 is a flat solution of the Chern-Simons field equations with trivial holonomies. So this means that I can always parameterize it like this, where now G plus and minus are group elements of the SL2 group. And like this, I obtain a connection which is SL2R valued, and this is the object that I had within my Chern-Simons formulation. So that is the first step. The next one is to define a single SL2 group element by taking the product of these two. So here, essentially, you can take this again as another trick, but it's just somehow I'm saying that ADS3 is just, oops. It's just a quotient space. And here I'm quotienting out the diagonal SL2R, which is nothing but the Lorentz group, since SL2R is like SO1, 2. And so you can interpret this object as being just a representative of the quotient, essentially. And once I arrive up to this stage, so I have a group manifold, and well, it's kind of standard how to give a Riemannian structure to a group manifold. And the idea, for instance, is that you can introduce a vielbein just by defining this object, and you can verify that this vielbein is just the same vielbein that you constructed in the Chern-Simons formulation up to a conjugation by a Lorentz transformation. So this means in particular that this vielbein can reproduces the ADS3 metric. So essentially all the structure of the ADS3 manifold is encoded into this group manifold parameterized by this object G. And other important step in this construction is that now, once we arrive at the level of SL2 parameterizations, isometries are kind of implemented in a trivial way, in the sense that the isometries of the ADS3 isometries are implemented as left and right multiplications of the SL2 manifold by suitable SL2 elements. And well, this kind of given this way of choosing the representative, essentially I can implement this transformation just as being left multiplications in, if you want, in the Chern-Simons formulation. And so the whole story will be to kind of translate the previous construction in terms of isometries implemented as multiplications by SL2 elements, and try to generalize this construction to SL3 in a proper way. Sorry. Okay, so let's go back, for instance, to the example of a massive point particle that I shown you before. So, for instance, we can consider a global parameterization of the ADS3 metric by introducing this coordinate system, and from this choice of coordinates, you can reconstruct the Chern-Simons connection, and from the Chern-Simons connection, you can reconstruct the group elements. And in particular, you obtain that the group elements take this particular form, where this T0 and T1 are just some generators of SL2R of the algebra in this particular basis. And as a result, the SL2 manifold, which is isomorphic to, at least locally, to the ADS3 manifold, is parameterized in this way, where you can see as a parameter the coordinates that appears also in the matrix, so T, phi, and chi. So chi plays the role of the radial coordinate, so it will be, to a large extent, completely irrelevant for what I'm gonna to do in the following, while all the important information will be stored in the behavior of T and phi, essentially. And the isometry that we used to build a point particle by doing identification of points in this formulation can be rephrased in this way. So as in the general case, this is just a left multiplication of a group element giving the Chern-Simons connection, and the particular form of a connection is just this one. And well, you can easily see why, because like this, I'm just shifting T and phi as I did in the metric formulation. And once I did this step, I can go back and reconstruct the connection that I obtained after the identification of points, and reperform the same change of coordinates that I did in the metric case. I don't show you the details, but you can trust me that at the end of all this procedure, you obtain connections that take this form. And now, now I introduced also this other basis of SL2 that will appear often in the following. So the main unpleasant feature of these, of the result of these manipulations, that you obtain connections that are not in the highest weight gauge. So if I want to avoid to pass through the metric, I cannot read off directly what I built with this procedure just by looking at the result. But in this particular case, you can easily save the whole procedure, because you can find easily a gauge transformations which brings you in the highest weight gauge. And in this particular case, moreover, the gauge transformation is kind of trivial, because it just it can be interpreted just as a shift of a radial coordinate, essentially. And after you perform this gauge transformation, you obtain the connection in your beloved form, where it's clear that what we have described is just a connection that has the generic that satisfy, for instance, the boundary conditions usually considered in gravity, and from where you can read the mass and angular momentum, and the expression for M and J are the same that I presented before. So in particular, there is a negative mass, and you can understand from this that here you recovered a conical defect singularity. So here and in the following, I just showed essentially the A phi components, because it's the one that is usually relevant to understand what are the charges of a solution that you have obtained. And moreover, AT, in this case, it's kind of, it's whatever, but recall that I'm still in Lorentzian signature, so my time coordinate is not wrapped, so I can rescale it and absorb any potential, any chemical potential that appear into the story, so without any problem. No, where they are, sorry. No, at least they are not written in the... yeah, they don't. No, so you just have to perform a gauge transformation in order to go to the standard gauge, to the standard... Sorry? Not in this case, no, because it's just a radial gauge transformation. No, well, I know that I cannot do the most general gauge transformation, but the point is really that the gauge transformation that you need to go in the highest weight gauge are exactly of the type that don't turn on charges. This is true, so that's, well, we haven't looked at these to see, but I mean, the highest weight gauge is just a useful tool to classify the solutions, but it's not somehow completely mandatory, no? For instance, you can have any upper triangular gauge. This is probably not even in that case, because I have something which is not 1 here, but I mean, in principle, as you use gauge transformations that are kind of legal, so you can do that. I agree. This is legal because essentially it's just a redefinition of chi, of a radial coordinate. I mean, it's legal up to subtleties, so there are some recent works that say that it's not completely legal to do these. Well, at least at the black hole horizon, but... No, that's I don't think so. No, because I'm not claiming that I have to include somehow this solution. So I'm simply consider a different gauge. Okay, no, but Okay, no, this is true. So as is the usual trick, no, you can play with different kind of boundary conditions and use something different. So here the philosophy is whatever I obtain, I always try to bring it back to the eigenstraight solution, because I want to be to have a standard three-dimensional eigenspin theory. So maybe it will be interesting to look directly at them, but somehow it's not what we are doing at the moment. So it's a very conservative viewpoint. So I'm not producing anything new. I'm just providing a new way of producing what is known, essentially. And well, related to this, so what I want to do with, no? Because essentially, as you can, as the discussion is saying, so I'm not producing anything new, and so what I want to extend is this group SL2 group theoretical approach to eigenspins. But why one wants to do this? Essentially, since the Euclidean approach works so well. So, at least in my opinion, there are two motivations. So one motivation is to try to understand better eigenspin geometry. So, for instance, defining how causality is defined in the context of eigenspin is not clear, is not completely clear at the moment, at least. And here you can hope, or maybe you can dream, to obtain notions, constraints on causality, or hints about how to define causality in eigenspins, just by looking at the group, the structure of the groups SLN. So, for instance, you can define geodesics and so on, and you can hope that this gives some hints on causality in eigenspins. So of course, it cannot be as simple as classifying geodesic in SLN groups, because, for instance, you have to pick up an embedding of SL2, so you have to decide where is gravity, and then the notion of causality should depend on this embedding. So, I mean, this is kind of dream for the future, but you can have even a more pragmatic viewpoint, and just saying that one advantage of this approach that passed through identification of points in an SL2 manifold is that it's kind of easier to identify, to play with multiple objects, with multiple particles, for instance, and to have kind of and to study kind of dynamical processes. For instance, you can consider, it has been done in this pioneering paper by Matchul, you can consider the collision of two conical particles, and in some cases, as the one depicted in the picture, this collision creates a black hole. So, for instance, this could give a way to study from a bulk perspective phenomena like thermalization in CFT and so on, because here you can you can create a black hole by using this kind of approach, which is something that is not so trivial to do in the eigenspin context, where, for instance, it's not so easy to characterize matter, or at least it's not so easy to characterize matter in a context that is as simple as Chern-Simons, essentially. And, well, if you want, you can even generalize and consider multiple scattering of particles, take limits where this become a thin shell solution, and so on. So one direction, at the moment I don't have confirmed result to report, so this is the part which is in progress, but you can hope to use this kind of formulation to consider dynamics. So now, up to now, I just discussed about gravity. So let's move a first step ahead, and let's add a U1 Chern-Simons fields to see how how to characterize the trick that I would like to use for eigenspins. So the idea is that we start again from a patch of anti-de Sitter tree described by a certain group element, and we introduce a U1 generator. So we introduce a generator that we assume commutes with a SL2 generators, and then we consider an extended manifold which is parametrized in this way. So we take our beloved parametrization of ADS3 and we just add the extra generator with a certain parameter that we would like to interpret as a coordinate in an extended manifold. Then we can look at the field bind on this group manifold and expand it along the generators of the algebra associated to this group, and we will have a component that is along SL2, the SL2R algebra, plus a component along the new generator, essentially. And if you confine yourself at looking, taking derivatives only along the coordinates in ADS3, nothing changes essentially. So the field bind remain the same as in gravity, and here you obtain 0, and you can see because essentially this object is obviously invariant under a shift, a left multiplication by a constant element of the algebra. But thing changes if you include, if you also allow yourself to derive in the parameter that you add. So you don't interpret it as being just a parameter, but you interpret it as being a new coordinate. Well, in particular, in this ADS case, you have that the field bind, the component of the gravitational component of the field bind along the new coordinate is 0, but you get some extra contribution. So something is changing if we introduce the theta coordinates. Up to the moment, this is just a kind of curiosity, but now I want to play with the theta coordinate in order to build a solution. And so at the stage I presented it up to now, so we just had essentially an ADS3 cross R manifold, and I can say that I just throw away R essentially, and I go back to my gravitational theory. But I can also consider an extended isometry, which now involves also the additional coordinate theta. And the form of isometry is just a shift, so it's very similar to what we have done before to build the conical particle or the black hole. And the only difference is that after I perform this isometry, essentially the manifold, the quotient that I obtain is no longer of this factorized form. So I cannot say trivially that I throw away the R coordinate. And so the meaning of theta is a bit doubtful. But on the other hand, I can play again a similar trick as before, and I kind of I redefine my coordinates such that the isometry acts trivially only in the angular coordinate, so only in the coordinate phi, that was the angular coordinate in the ADS3 solution. And after I do this, I obtain again a manifold which is of the form M cross R, where M is just interpreted to be ADS3. And the difference is that now my the component along the ADS coordinates of a small a now is different from 0 after I perform this change of coordinates, and I would like to interpret it as being as being the U1 field associated to the fact that I'm considering also Chern-Simons U1 theory. And indeed you can check that this object what you produced in this way is a flat connection, and you can use this flat connection to show that your solution is now carrying an electric well, a sort of electric charge, because it's a Chern-Simons charge, essentially. And so the whole idea is to use the same kind of trick in a context where your manifold has a structure which is more complicated as being just ADS3 cross U1, but the main idea is the same as the one that you can find here. So let's move to higher spins, so at the end. And so what is the general recipe that I would like to use? So the idea is that I would like to take my SL2 manifold, which describe a certain patch of ADS3, and in particular I know that I can build, that I can choose a patch such that I can build a solution like conical defects of black holes just by performing identification of points along certain isometries, which is represented by this scaling vector naively delta S. And the idea is to introduce additional coordinates and to interpret them as being and promote the parameters of additional isometries to become coordinates on an extended manifold. And in order to try to recover a solution to be interpreted as a black hole or as a conical defect, the idea is to allow only for isometries that commutes with isometry that I use to build my black hole or conical defect solution. So in particular that they commute with delta t and delta phi, essentially. And then you consider the extended manifold, which is spanned by all these coordinates, including the parameters of a new isometries to be interpreted now as coordinates, and then you consider the quotient where you identify points under this isometry. And well, under an isometry which is a suitable linear combination of the isometries that enter the game, so the gravitational one plus the additional ones. Then the last step of the recipe is that you take the result, you put it in a factorized form, where M1 is something that you interpret as a patch of ADS tree, and M2 is whatever remain, essentially. And you choose your change of coordinates such that M2 is such that I acts trivially on it. So essentially you want to throw everything inside the identification of the angular coordinate phi. And at the end, you can reconstruct your Chern-Simons connections, for instance, just by deriving from G plus and minus, deriving A plus and minus, and check what you get, and see if this procedure gives you a black hole, a conical defects, or whatever. So let's look at the case of a spin tree black hole. So in this case, the starting point is this particular parametrization of SL2. So well, you can think at it as a sort of Euler angle parametrization of SL2. And well, you can show that starting from this group element, just by considering shift in T and phi, you can reconstruct a black hole along the lines that I followed for the conical, for the massive point particle. And once you are there, you add 2 extra coordinates. Why only 2? Because, well, I already anticipated that is the best that I can do in this context under the following assumption. And the assumption is that the additional coordinates are introduced by looking only at isometries which commutes with the isometry that I used to build a BTZ black hole. And in this particular case, this condition, so you want to introduce isometries which commute with these 2 killing vectors, and this implies that this matrix here must commute with T2, where T2 is again an SL2 matrix that appears inside the expression. And this gives a unique result. So if you impose this condition, there is only one matrix which commutes with T2. And here to explain the notation, so I'm just using the customary basis of SL3, which is presented like that. And so these beasts, WM, are the matrices that appear in this point. Okay, so that is not a very important detail, but the important detail is that I added this isometry, so I performed a left multiplications by this group element, and this group element is specified completely by this particular matrix. Yes? Sorry? No, so implicitly. So here I'm playing a trick that I just add some pieces that I can interpret as being a sub-manifold of a group manifold. So the main problem is that I don't have yet a view on the full SL3, essentially. So here I need only what I need to build. Not yet. Not yet. So I'm just building it piece by piece. So I am adding only the pieces that I need in order to build the solution. That's, of course, the hope is to have a control over the full SL3, but at the moment I don't have it. This is true. So, I mean, at a philosophical level, I have it, but, well, one thing is writing this. I can put a 3 instead of 2 and telling you that I'm working with this manifold, but one thing is to really work out the details. So the details are not yet, but at the philosophical level, I agree. So what I want is exactly this object with 3 instead of 2. That is definitely, that should be a sort of, a bosonic superspace from where you reconstruct Chern-Simons in a sort of rheonomic approach, like in the old supergravity days. So that is the philosophy behind, but at the moment I'm only presenting you the part which is solid, not. Okay, so now let's go back at the construction of the solution. So now I want to perform this identification or this isometry, and again I put on top of this isometry a change of coordinates that let the isometry act trivially, so in the sense that now at the end it acts only in the angular coordinate. And well, that is something that I can do, and now I can compute the connection and see what I get. And the only thing is that the connection depends on four constants that I would like to interpret as being the charges versus chemical potentials, essentially. And exactly this number is the right number that I expect for a black hole solution. So what are the properties of a solution that I built in this way? Well, first of all, if you just naively compute if you just naively compute the connection, you obtain this expression that is not very illuminating. So you face the same problem that we had before. So it's not in the highest weight gauge. But you can at least start doing at least one observation is that it depends on all four quantities that we introduced, alpha, tau, q, and w. And another thing, for instance, that you can do is to take this solution and compute the holonomy around the angular circle. And this gives you a first nice indication that what you have done is not completely crazy, because you discover that the holonomy has real eigenvalues, which is a property that you expect for a black hole. So up to this point, we are going well. But you can do even better in the sense that you can find explicitly a gauge transformation, which is a mess, so it won't be shown on the slides. That brings you in the highest weight gauge, but you can find it. And at the end, what you discover is that you have a certain parameterization of L and W, and which are a certain parameterization of the charges. But the nice thing of this parameterization is that it allows you to satisfy the relations between the charges that you expect to have in a black hole solution. So, and these kind of relations can be obtained by asking that the entropy is real. In this case, they are produced by the procedure of identification of points. So this seems that we are in the going into the right direction. And it's just automatically satisfied by the parameterization that you have there. And probably this is, you're not used to this, it's just that I'm using crazy normalizations. But the important thing is that the bound is satisfied. Yes, it's automatic. Well, at least one is obvious to see, the fact that this object is positive, because it's a sum of squares, and my parameters are real. The other one is less obvious, but I can guarantee you that it holds, essentially. But at least you can appreciate this one. And and this is parameterization. With this procedure, you get this parameterization. So, and then, well, another things that allow you to understand that the procedure seems to work well is that you can ask yourself what happens if you want to build a conical defects. And essentially, you follow exactly the same procedure with a tiny difference. And the difference is that just in the pure gravitational case, if you want to build a black hole, you start from the connection that I showed you with the group element that I showed you before. While if you want to write a conical defect, it's much better to work in another coordinate system, because these coordinates span exactly the patch that you have to cover in order to obtain a conical defects. And although they seem the same, they do differ in the sense that here you have different SL2 generators. So this means that in the case of a conical defect, you can follow the same procedure, but apart from one difference, and is that now the matrix W that you obtain in order to get the extended manifold must commute with T0 and not with T2, and that is the only difference. And then you follow exactly the same procedure, and you get something that instead satisfies the constraints on the charges that you expect for a conical defect. And so, well, now let me try to summarize what I showed you. So the main thing is that it's possible to build with this procedure, although at the moment it looks a bit ad hoc because we don't have a true complete superspace interpretation or bosonic superspace interpretation, but at least with this procedure you can build black hole solutions and conical defects. And one thing that it's maybe I haven't stressed before, one thing is that you can build them directly in Lorentzian signature, so you don't have to pass through the Euclidean formulation. It's true that if you want to compute entropy, well, at least the best way that I know to do is to go to the weak rotate in order to compute the Euclidean action. So, but well, at least as far as you would like to build the solutions, you don't have to do this. And well, as we briefly discussed, this procedure, as I presented it right now, essentially add one extra coordinate for each charge or slash chemical potential, and it will be nice, as it has been asked, to reconstruct the full SL3 by kind of generalizing this idea. And well, another advantage is that here I described always a massive particle at rest or a static black hole, but it's kind of easy to boost it, because you just consider well, essentially, for instance, in the case of a particle, if you want to describe a moving particle, here I did identification of points that were essentially where the stability group was just a geodesic of a particle at rest. So if you evolve in time, this was the picture that I draw, and time runs into this direction. But you can just consider the isometry whose stability group is the geodesic of a particle in motion, and you can do the same also for a black hole, and with this kind of procedure you can also consider massless particles, for instance. So this first step is kind of simple, and then you can ask yourself if you can perform also the other one, so to consider particles that now are moving, but they are also colliding and creating black holes, essentially generalizing the picture that I showed you in some previous slides. And so that's the main things. Thanks for...
So, yeah, for the one comment just first, because you said,
yes.
Oh, the entropy I can only define it in Euclidean. You can also define it in Lorentzian.
Okay, so
you will just use the Wilson line around the phi circle, and that will, at least it will
okay,
reduce the entropy.
okay.
So that.
Okay,
good.
that is good. So that is another item.
And it will give you the same expression as
okay,
the sum
yes,
of the
yeah, this is
eigenvalues,
true because yes.
But yeah, but now, right, so it's really nice you have a Lorentzian definition
yes.
Of this black hole, but what happens to the time component?
The time component is just, okay, so this I avoided to put a slide exactly for that, but I was expecting. So the fact is that the time component is kind of a mess, but the things that you can do is to slightly modify the gauge transformation that I showed you.
No, but how do you, because there's some, like the equations of motion will tell you it has to commute with the other component, but how can you see that the components have
well, essentially the idea is that by performing, so think at gravity. In the case of gravity, in Lorentzian you can either put the chemical, the chemical potential has kind of no meaning in Lorentzian signature because you can rescale it by rescaling the time coordinate. Now the advantage is that I have a number of coordinates that I can rescale, which is equal to the number of chemical potentials.
But you still, like, you have a connection, you did that, and so now you have this connection on
yes.
the 3 part. But do you see that you get the connection, the same time connection that you would have got if you did the Euclidean definition of the
yes,
black hole?
not with the gauge transformation that I showed you, but with a slightly more complicated one. Sorry, with a change, not with a change of coordinates that I've shown you, but you can modify the change of coordinates such that it still brings you a result where the isometry acts trivially in phi, but now the form of t of AT is the one that you expect from the Euclidean formulation. So essentially there is a freedom in the gauge of coordinate. I've shown you the simplest one just to kind of propagate the simplicity of the previous manipulation, but there is a freedom there, and this freedom you can use to tune as you wish the chemical potentials essentially. Okay. So naively the idea is exactly that you are not allowed to do it usually in the standard formulation because you don't have enough coordinates. But here you have more coordinates and a freedom to perform reparameterization of them that will allow you to absorb the chemical potentials.
Now, also related to the question that Michal was asking, the group manifold of SL3 is way bigger.
Yes.
Like it should be
yes.
Yes. So wouldn't you expect to have way more different quotients?
Well, no, I think, yeah, you can have more quotients, but the problem is that they are physical or not. So here I'm trying to be ultra conservative, and I only add isometries which commutes with isometry that I use in gravity to build solution, and well, that could have been considered just a working hypothesis, but is enough to reproduce everything. But for instance, you can classify all possible conjugacy classes and so on, and see where the operation that I made fall, and they fall in a certain specific class, but there is way more. The problem is that for the other solution, I don't have at the moment any interpretation which makes sense. I don't know, maybe you produce other branches, the ones that are not connected to the BTZ or something like that, but at the moment it's not completely clear to me. So that's this is why I prefer to keep this very conservative approach. But these are just some conjugacy classes in SL3, which gives you the solutions and which are natural generalizations of the conjugacy classes that gives you the black holes and the conical defects in the case of gravity. And well, also this is another things that I haven't showed, but you can also understand where are the classes which gives you extremal solutions, for instance. It's because it's part of the story. But yeah, like this, with a known solution, you don't span all the conjugacy classes. The other one, I don't know what they are.
Background. So can you, how do your results tie in if you go to the Euclidean setting with what you would get in, via that method?
Well, if you go to the Euclidean setting, what do you mean? So if I try to put the additional coordinates in the Euclidean setting?
Well, I mean, you said it's the Lorentzian ADS3 you are discussing the black hole.
Yeah, but you can, well, I can take the result, which is a Lorentzian black hole, and once I have a Lorentzian black hole, I can Vic rotate to a Euclidean, I get the same solution that people already know. So in this sense, I'm not adding new on this perspective, and so at the moment, I don't have new insights on these on this kind of properties. The only thing that it's another thing that is not yet completely clear to me is that you can think of absorbing the chemical potential in Euclidean signature inside the periodicity of the additional coordinates. And these, you can try to think that this gives some sort of, so that your theory at the end is defined on an higher dimensional torus, and then you may try to argue that this puts additional constraints on the partition functions, but at the moment these are as wild speculations as the full super, so I don't know. So it's quite natural of try to move in this direction and try to define higher dimensional tori. That's, I agree, but I haven't looked at the details, if this can bring some constraints, if this is completely consistent to compactify all of them. So at the moment I don't know, but it's definitely a very good question and interesting direction to explore. So. Sorry, first law?
For this class of black holes?
No, so at the moment we just reproduced what is known with this different perspective. So in this sense we don't know more about thermodynamics with respect to what people already know, because it's, I mean, so there are many questions clearly. So there is a new, and kind of pushing forward this new viewpoint, and then you can try to see maybe some things are more natural in this kind of viewpoint. I haven't thought these, so I had in mind more this dynamics or superspace or something like that, but it could be that there are indications also in this direction. I don't know, unfortunately.
Okay, so that's next.
Thanks.